things like this. So the idea, I want to try to just describe some questions which might be interesting and would be possible things to look at. So I'll start with just a summary of VC dimension, VC density. So you may know all this, but so we have a X curly F. Sorry, there's a pen's bad. Another one. A set system. So this is not really model theory, it's just combinatorics really. So that means that X is a set and F is a collection of subsets of X. So F is contained in the power set of X. So that's the power set of X. So that's what I mean by a set system, a system of subsets of X. And then a key bit of notation for a subset of X, we write F intersect A. So this is just an abbreviation, it's a sort of abusive notation. This just means the set of all things of the form capital F intersect A, where capital F is a subset of curly F. So the picture, we've got X here, we've got a collection of subsets. These are my sets in curly F. And somewhere I've got A, this is A, and we're looking at all the various intersections of sets in F with A. So it's things like that, 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 and that. That's sort of the picture. Okay. So this is the, if you like, this is the set system induced on A by F, by intersections with F. Okay. And then we say A is shattered by curly F if F intersect A is the whole power set of A. In other words, every subset of A arises as an intersection. So that's size 2 to the A. Typically, we're thinking of A as being finite. Maybe I should say, we really are thinking of A as being finite. Okay. And then if say F is non-empty, okay, then the VC dimension, Vapnik-Chervonenkis dimension of F is going to be the supremum of the sizes of the sets A such that A is shattered by F. So it's the largest possible size of a set shattered by F. And this supremum is meant to be in N, or if there is no largest natural number, then just be to infinity. So that's how it's interpreted. And F is a VC class if I have my space, VC dimension of F is in N. So there is a largest size set shattered by F. Okay. So I mean, this is this notion introduced by Vapnik and Chervonenkis around 1971, really in statistical learning theory, led into neural networks. The idea is that there's a very nice statistical kind of result about probably approximate correct learning, which underpins it. I won't go into that. I won't say anything about the connections to machine learning because I don't know about it. I don't know enough about it, but it is a nice subject. I don't know, with the connections to machine learning, I don't know how much that's still active, or whether it's an old subject. You know, because machine learning, of course, is a very big, new, trendy subject. And I don't know if they still use these ideas. But there's another side that definitely is being used for applications, which is more in algorithms in graphs. So obviously, as people, you know, with very fast computing, you can model many situations on a graph. You know, model an epidemic or something. And people want to have good algorithms for graph theory, and there are good connections between finite VC, a bounded VC dimension, and good algorithms in graph theory. Okay, so that's the first definition. So another definition. We define a function pi curly f from n to n by pi curly f of n is going to be the supremum of the set of all f intersect A, size of that, where A is contained in X and the size of A is n. So we look over all subsets of X of size n, and we ask, how much can we shatter them? And the biggest amount of shattering gives the value here. So this is called, the pi f is the shatter function of f. And so what you're going to get is that VC, the VC dimension, I guess dim of f, is the supremum of the set of all n, so that pi f of n equals 2 to the n. If you can completely shatter a set of size n, you get 2 to the n here. And that corresponds exactly to saying, so remember this is the supremum of size that A is shattered by f. And for A to be shattered by f just means you get 2 to the n for pi f of n. Okay. And so that's all very standard. But now there's a surprising result. So this is the Sauer-Scheller sort of dichotomy, I guess. I think there are other names also, maybe Pearls or something. Maybe not just Sauer and Scheller. So it was, I put a hyphen there, but it's independent. It's around 1971. So Sauer is a combinatorialist. You know Scheller. So this is totally independent, but at the same time. So Scheller didn't know about VC classes, I think. He was just thinking about NIP. Sauer was from the point of view of set systems. So this says either 1 pi f of n equals 2 to the n for all n. So this means, so curly f is not a VC class, because you can shatter arbitrarily large sets. Or, and this is the kind of, I think, surprising thing, that pi f is actually bounded polynomially. So you get that pi f of n is less than or equal to n choose 0 plus n choose 1 plus dot 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 plus n choose d, where d is the VC dimension of f. And this is the case when it's a VC class, so this is where it's in natural numbers. So in the infinite VC dimension case, of course you just get this, but the real point is that if you have finite VC dimension, then this function is bounded by this, and this is less than or equal to this whole expression is less than or equal to, I think, E n over d all to the d. So it's polynomial degree d. So the real point is that for a VC class, the shatter function is bounded above by a polynomial of degree d. So d, so E is just the natural logarithm, the usual number E. Okay. So now we can define VC density. So this is, I'm going to use a small VC of f. So it's a lowercase VC rather than uppercase. VC of f is going to be the infimum of the set of all R in R, positive reals, such that pi f of n is big O of n to the R. So that's in the case of finite VC dimension. So that's, I'll just move the space. This is if VC of f is finite, I guess VC dimension of f is finite. So in the case where it's finite VC dimension, it's the biggest R such that this is bigger of n to the R, and it's just going to be infinity otherwise. So the idea is that this is the degree of the polynomial growth of pi f. We know that this is bounded above by a polynomial. We're asking what's the actual degree? And the actual degree, because polynomials by definition have integer degree, natural number degree, but we're allowing here fractions or even irrationals. So we have this definition here. So it's really saying, another way of saying this is to say that pi f of n over n to the r is bounded. Right. Do I mean that, or do I mean the other way around? Yeah, I guess I mean that. Yeah. Yeah. So it's the smallest, or the infimum of the r, so that pi f to the n over n to the r is bounded. And so automatically, VC of f is going to be less than or equal to capital VC of f. So this is the density, and this is the dimension. And the idea, the reason why I think this is interesting is that, well, they're slightly different measures of complexity of a set system. So both measures of complexity of f. Perhaps little vc gives more information than capital VC. And also, sometimes little vc is easier to compute. We seem to, at least in things coming from model theory, we seem to have more methods for finding VC density. So that's sort of the background on this. So the model theory connection. Sorry, Rosie, I need to adjust the camera. Sorry. Yeah. The model theory connection. So this was really first noted by Laskovsky. I think he went to a kind of statistics talk in Berkeley, a colloquium, and realized the connection to NIP. So suppose M is a structure. We really mostly work with structures rather than theories here. Phi x bar, y bar, a formula in some language. And we'll just say the length of x bar will be m, the length of y bar will be n. Okay, so let x be m to the m, and f sub phi will be the set system in X determined by phi. So it's going to be the set of all sets of the form phi m to the m a bar, where a bar is in m to the n. So this is a set system. So X f phi is a set system. And now the observation is that phi x bar y bar as a formula is NIP if and only if X F phi is a VC class. Oh, it has finite VC dimension. So there's a slight, I always get confused here when you define the idea of an NIP formula as to whether you're shattering the x variables or shattering the y variables. But in fact, phi xy is NIP if only if phi star yx is NIP. It's not too important, but well, you have to be a bit careful about the order of x and y here. But I won't worry about that. So this is immediate. This is just by definition of NIP. Of course, usually we talk about NIP theories where all formulas are NIP. But it makes sense to talk about a single formula being NIP. A theory is NIP, and it just means that all formulas are NIP. Okay, so then we can write. We can write. Say capital VC of phi for VC dimension of I guess X F phi, and little VC of phi for the VC density. Sorry, that will be the small VC. This is the density, so it's just little VC of, I get, well, just X F phi, or just F phi. So we can talk about the VC density of a formula. So then the general question, the sort of question for model theorists is, can we compute VC of phi, or capital VC of phi, in particular cases? Say looking at NIP theories. There are other questions too, of course, but that's a natural kind of question. I think the first place I know of for this, there was a paper of Karpinski and McIntyre. I think it was around 2000. And they showed, for example, that I guess the main result of this was that if T is O minimal, then VC of the formula phi x bar y bar is at most the length of y bar. It's quite surprising because you've got a set system in the x variables. In the x variables, m, the length of x, could be arbitrarily big, right? But it's saying that the VC density, this kind of degree of growth of pi phi, is at most the number of parameter variables. And then there were a couple of papers of Aschenbrenner, Dolic, Haskell, myself, and Starchenko. So 2 papers, I mean, I think they were, I forget the title, but they were, the first paper was Trans AMS 2016. And the second paper was Notre Dame Journal of Formal Logic 212. So it's a bit strange the other way around. But, so I think this was the longer paper, took longer to referee. We took a bit longer to write as well. But this was really the more fundamental paper. This was a special issue for Pilet's 60th birthday. So they're quite long papers, quite a lot of results in them. But for example, so examples of results. So in one, we show things like we extend this result to weakly minimal. So if T is, I think we show actually weakly quasi-minimal. T was, well, T equals a theory of M. Then VC of phi is less than or equal to the length of y bar. So when I started here, I said M is a structure. I didn't mention the theory, right? But I've mentioned a theory here because we don't know if every weakly minimal structure is NIP. But if the theory is weakly minimal, then it's NIP. Weakly quasi-minimal, that means that every definable set in one variable is what, is it a Boolean combination or a union, I forget, of 0 definable sets and convex sets. Maybe it's a finite Boolean combination of 0 definable sets and convex sets. And there were other results. So, for example, if T is the theory of the p-adics, the p-adic field, which is it's very common, things you can prove about the reals or about the minimal structures, you can often also prove about the p-adics. They're very similar. So then VC of phi is less than or equal to twice the length of y bar minus 1. Maybe we can show y bar. Maybe it's true for y bar. We don't know. And then there are other results. And then in the second paper, there's slightly different kind of results. So more of a stability kind of result. So if T is NFCP of finite U rank D, then VC of phi is less than or equal to D times the length of y bar. So there's a connection to U rank. Sorry, I'll go back to this board. So there are quite a lot of results finding VC density bounds. And there have been more papers since then. For example, there was a student, Bobkov, a student of Aschenbrenner. He had various results, but for example, similar results for trees. I guess this is trees in the sense of partial orders, so some meat trees, things like that. There's quite a lot of other papers. Most of the other results are in algebraic contexts, so valued fields, things like that. But the one question I wanted to ask was, find similar bounds for VC density in O-stable theories. So, obviously, I don't really know about O-stability. I mean, Victor's the expert. But as I understand it, there are various definitions of more general concepts. But the basic starting point, so O-stable ordered structures, these are NIP, and they sort of, I think, as I understand it, it's combining ideas of stability and orders. So you bound the number of types within cuts, basically. So you're bounding stability and orders. So we have some methods for handling ordered structures, and we have some methods for handling stable structures. So maybe these methods can be combined or maybe, I don't know, maybe O superstable, I don't know. So e.g. combine methods for ordered structures and stable structures. A couple of other little results I will mention. I guess these are from the first paper. So one theorem is that assume T n. Actually, no, sorry, I need more notation. Step back a moment. So we have a lot of these results where you bound the VC dimension of phi in terms of the number of y variables. That seems to be a common thing. So we can define VCT on the natural numbers. So T is a theory now. And the idea is that VCT of n is the supremum of the set of all things with form VC of phi, where phi xy is a formula and the length of y is n. So these are the results you just get n. T weak Leo minimal implies VC T of n is at most n, but actually it can never be less than n, so it'll just be equal to n. And T NFCP finite U rank D implies VCT of n is less than or equal to D times n. So this is also an interesting function to look at. So there are some so here we might be trying to, in this problem here, we could try to understand this function. I'll mention a couple of results related to this. So a theorem that if T is NIP, then VC T equals VC T Scheller. So that's the Scheller expansion where you add predicates for all externally definable sets. So Scheller proved that expansion is NIP. So it's very much connected to Vector's theorem about expanding weak Leo minimal structures by convex subsets. So, going to the Scheller expansion doesn't change this function. Another comment is that VCT of 1 less than 2, that's looking at a single y variable, that implies T is dp minimal. So this is sort of the analog of strongly minimal for NIP theories. That's the idea. So there's various results about this function VCT. There we go. So, I mean, I think part of this arose, as I understand it, so looking for, hi, morning. We're looking for maybe areas of application of NIP, applications of NIP in some sense. So there's quite a literature really in, say, graph theory by computer scientists related to VC dimension and VC density. So, I mean, these are computer scientists. They're interested in classes of graphs, maybe somewhat restricted classes of graphs, in which algorithms work well. In other words, there are polynomial time algorithms, maybe polynomial of low degree, things like that. There may be algorithms for testing whether a given graph in the class has some first order property. Or sometimes they're working in slightly bigger logics beyond first order. So it's very much connections between finite model theory and graph theory and computational complexity. And you can imagine it's maybe driven by algorithms on graphs, algorithms on networks, data science, you know. So there's a lot of interest, and there are some strong people working around this. I'll just mention, in case you're interested, I just started, I don't know this literature at all well, but I just started Googling yesterday, just a few papers, just as a sort of starting point. Maybe I'll write down some papers that, if you're interested, you could look at. So there was something by A. Pajka and M. Pilipchuk. I don't know these people. So this was 2020. And it's VC density of set systems definable in tree-like graphs. So in finite graph theory, they have lots of conditions which make graphs in some sense tree-like. They talk about clique width and tree width. Some of these started with work of Robertson and Seymour around 1990. The most important papers in graph theory were by Robertson and Seymour around 1990, a string of very long papers proving the graph minor theorem. And they came up with the various notions of tree-like. And in tree-like graphs, there are good algorithms. So they're looking at VC density. I think they're interested not just of first-order formulas, but also of maybe monadic second-order formulas in slightly richer logics. There's another paper, Pilipchuk seems to work a lot on this. Another paper I noticed of, Pilipchuk, as above, Sieberts, and Torunchuk. These are all people who work in this kind of area. So this is on the number of types in sparse graphs. So I think this was 2018. So sparse is a bit vague. The idea is it's graphs where the number of edges is somehow low. It grows slower than quadratic in a number of vertices. And there's a particular notion, nowhere dense, which is very close to monadic stability. And so there are nice connections to model theory of this. And they're counting types. And counting types is very closely related to finding VC density. And that's a key point. That's why VC density is easier to work with than VC dimension. It's because finding VC density is basically the same thing as counting types, in some sense. So there's this, and there was one other paper I was going to mention. Sorry. So this was by E. Bonnet, F. Foucault, I think, and a Finnish name, L. Lehtila, and A. Parot. So this was neighborhood complexity of graphs of bounded twin width. So twin width is a very trendy thing in graph theory in the last 7 or 8 years. Lots of papers on finite graphs of bounded twin width. And it's very close to monadic NIP. Yeah. It tends to be, I mean, here it was monadic stable, here it's monadic NIP. I think if you're looking at ordered graphs of bounded twin width, that's exactly the same as monadic NIP. Obviously, we're talking about finite graphs here. So it's kind of uniform across the family of finite graphs. You have to kind of phrase it right. But there's a close connection to monadic NIP. Yeah, so that means that any expansion by unary predicate is NIP.
But it's continued to be NIP.
Yes. But we're talking about a class of finite graphs. So you can think of the ultra product, if you like. You can, when you say a class of graphs is stable, it's really the same thing as saying that every ultra product is stable. So it kind of makes sense.
Who introduced this notion for NIP?
Monadic NIP, well, Baldwin and Scheller in the 1985, they talked about monadic stable. And I think then Scheller did something on monadic NIP. But I think the important papers were the recent ones by Braunfeld and Laskovsky.
For stable, this is reduced for what notion? Trivial?
It's going to be close to that. Yeah. I mean,
trivial forking, yes? No?
Yeah, it's that essentially that kind of thing. It means there's no kind of binary coding going on. So there's no algebraic structure. But essentially, if you look at, say, M just with equality, and look at M squared with the induced structure, M squared is not monadically stable. So neighborhood complexity, this is just that's just me. Complexity is another word for density, I think. So this just means the VC density of the set system V is the vertex set, and things are the set of all sets of the form E. Well, I'll just say N of A, where A is in V. So this is the neighborhood of A. So you have a formula saying, you're just using the formula for graphs, x adjacent to y. It's a quantifier-free formula for graphs. And we're just using the VC density of that formula, if you like. So just the set of all neighborhoods of vertices.
What neighborhood here is what?
The vertices adjacent to A. So equals a set of x. Yeah. So yeah. So if you think of your graph as given by a binary relation EXY.
Graph symmetry, yes?
Yeah, symmetric graphs. We're talking about symmetric graphs here. If we're given by a binary relation EXY, then we're just talking about the VC density of this formula. So it's really the VC density VC density of this formula here. So that's what this paper here is about. So it's VC density of this formula in graphs of bounded twin width. So my purpose was to kind of give some questions, really. So I mentioned that question about VC density in O-stable theories. I'll just mention one other question. So let's fix, say, a prime power q and 1 less than k less than n. Okay. And so we have the vector space V n q. So that's just it's a finite vector space. Dimension n over fq, the field of q elements. Field of q elements, finite field fq. Okay. Form a graph G where the vertices are the k-dimensional subspaces of VNQ. And we'll treat the graph, with the GE. So this is the edge relation. So I'm thinking of it, this is a binary, symmetric binary relation. And we're going to say that E of, say, S dash. So these are both k-dimensional spaces, if and only if the dimension of S intersect S dash equals k minus 1. So if they're equal, the intersection is just S, so it's dimension k. But it could be k minus 1. So we'll form a graph like that. So my question is, find VC density of E. So that's like neighborhood complexity for graphs of this form. And certainly, if we fix Q and K and let N increase, this is certainly bounded. But I don't know how it behaves if Q and K increase. I don't know anything about this, but I think it'd be a nice thing to look at. It's a little bit connected to a paper I wrote with Adler and Benedictson, Icelandic, and myself. There was a similar paper, but we were in a purely combinatorial situation. There was no field, there was no vector space. It was just k-element subsets of an element set. So that's sort of like, that's a sort of second problem. Okay, I'll stop there. I mean, if you're interested, one or two of you, I could tell you a little bit more about some of the methods for finding VC density. But I'll stop there for now. So thanks. I'm sorry?
What about what method you?
Yeah, I mean, there was a certain, I prepared more, I could have said, but, so, sort of, my talk ended here, but there's more material on this VCD property and this condition U to DTFS. I can tell you a bit more about that.
Maybe today? No?
Yeah, sure.
How many
Yeah.
minutes?
Probably might take a bit of time, might take 45 minutes or so.
Okay, after coffee.
Yeah,
after
yeah,
coffee
sure,
break.
sure. So I'm assuming we're going for lunch today. The Ukraine is that good? The Ukrainian restaurant? So everybody everybody you can come. Yeah.
Ну, это уже фотография, то есть он разослал фотографию, все обесточили. А дальше, и там в основном проблема уже в этом. Жюли. Он такой тертый канадец. Я же против него писал письмо, знаете, да, подписано. Когда его президент.
Yeah, okay, so let's keep it very informal. So I'll try just to be half an hour. I don't want to be too technical, because but I want to say something about the method to prove the theorem that if, say, T is weakly minimal, then the Vapnik-Chervonenkis the density of the formula phi x bar y bar is at most the length of y bar. That's the result. So this is from this paper of Aschenbrenner, Dolic, Haskell, myself, and Starchenko. It's the first paper, the one in Trans-AMS. Sorry? Aschenbrenner, Matthias Aschenbrenner, Dolic, Haskell, myself, and Starchenko. So the basic idea is that you can think of VC density in a dual way, so it becomes counting types. So the idea is supposing we have X. Just imagine just for a moment, think of your formula phi xy, and you've got sort of X variables here, Y variables there, and you've got a set A. and you're trying to shatter A, and so you have some parameters, say B there, and say this set here is phi m b bar. Okay, and maybe you've got some different parameters there, and maybe this set is phi m b bar primed. So what we're really asking is how many intersections are there? But the thing to note is that phi m b bar intersect A equals phi m b bar primed intersect A. In other words, say this set here is the same as, say, this set there. Okay, those are equal if and only if the phi type over A of B bar equals the phi type over A of B bar primed. So we're in some sense, if B bar picks out the same subset of A as B bar primed. So if you want to calculate the number of intersections, it's very similar to counting phi types over A. So bounding VC density is related to bounding the number of phi types. And of course, counting phi types is something in model theory we're used to. We know how to do that sort of thing. That's sort of, I think, why in model theory it's easier to work with VC density than VC dimension. Because VC density is about counting types, really. But you're counting types in the y variables over the x variables. You're reversing x and y. Okay, so that's sort of the intuition. So let's see, get a bit more detail. So there's this notion of the VCD property we defined. So say delta a finite set of partition formulas phi x bar y bar, finite set of formulas of that sort. And then not delta is just going to be the formulas not phi for phi and delta. Okay. And usually we will assume, I think, delta equals not delta. So we close up the negation, I think. And then for B contained in M to the length of y, so tuples from M, delta x bar b bar, x bar b, will just be the set of all formulas phi x bar b bar. That's right. I'm assuming this. Yes. So I'm assuming if phi is in delta, then so is not phi. Sorry? Yeah. Yeah. I'll assume that. Okay.
Delta contained formula.
Yes. So if phi is in delta, then not phi is also in delta. That's what I'm assuming. It's just a convenience. So delta xb is just the set of all formulas phi x bar b bar, phi in delta, and B bar and B. So that's just notation. Just notation. So all formulas of this form, phi a delta formula, B bar a tuple from B. Remember, B is a set of tuples. So it's, okay. And then, so given, I guess we work inside some model. Work inside a model M. So given finite B, a set of Y tuples, as usual, a consistent subset of delta x bar B is called a delta x bar B type. Okay. So it's like a type over B, except that we're thinking of B as a set of tuples. That's the slightly unusual thing here. We think of B as a set of tuples. Tuples of length of Y. Okay, and so we're going to be interested in counting types, basically, or methods for doing that. And now, so maybe I'll just leave the statement here. So there's now a further definition. So given B inside M to the Y bar, and Q a, so that's just what I talked about here. This is just a set of delta x bar B types. So Q is such a type, okay.
B finite.
Yes, so B is B, yeah. So it's finite there, so finite here. So we want to talk about definability of this type. So this is
delta finite.
Yes.
Delta is finite set.
Yes. So delta is always a finite set of formulas. It's closed under negation.
Yes.
And B is a finite set of tuples. Yeah, that's the setting. So I think the nice thing here, there's a nice phenomenon that has emerged over the last 10, 15 years. Sorry. Yeah.
We want to go to the dimension of Lapsitz invariant.
Well, yes, it's more density. VC density, more density rather than dimension. That's where we're going. We're going towards this theorem here. That's it. I'm just giving you a little idea of the methods. Just not fully, but just a little idea of the methods.
But X is a tuple.
Yes. X is a tuple, that's right. And that's important. Because
So, for weekly or minimum theory, yes?
Yeah.
Right.
Yeah, I mean, that's really the point, that for weakly or minimal theories, it's easy to work out VC density if X is a singleton, a single variable.
Yes, because
For the usual reasons. And the point about, the result I'm going to talk about moves from a single variable to a tuple. That's really the point. That's really the idea. The thing to...
Это обозначение VC большое, это у нас dimension, а VC маленькое это
это dimension.
да. А маленькое
Здесь то же самое.
нет, это раз.
Ну, понимаете, там слабо минимальное. Это слабо минимальное. Там разделение не такое большое. Потому что там конечное число выпуклых, а если вы переходите на картежи, все равно будет, конечно. Там не так много. count VC
Yeah.
rank.
That's right. I mean, so the idea is that we bound VC density by reversing x and y and counting types, counting these sorts of types. That's the idea. That's the general idea. There's one thing general comment I wanted to say. Yeah, we have this classical sort of Shell result that a theory is stable precisely if every type is definable. We all know this, right? Every type is definable. There's a very nice version of this for NIP theories, which says that a theory is NIP if and only if this strange property UDTFS holds. That's uniform definability of types over finite sets. I won't define this. I don't want to go into this now, but it's the version of Shell's theorem. So a theory is NIP if and only if UDTFS holds. So it's types over finite sets definable in a uniform way. And it's an important thing about NIP theories. It's proved. I think was this Kaplan-Chernikov or Simon-Chernikov? I forget. It was the early 2010s, and he was using this idea of honest definitions. So it's in Simon's book on NIP theories. And what we're doing is a little bit, it was around the same time what we're doing. It's a little bit related to this, looking at types over finite sets. So anyway, so this is I guess, the definition I'm giving here. So given B and a type like this, a collection F, which is going to be a collection of formulas, say phi sharp of y bar for phi in delta of, this will be LM formulas, defines Q if, so I'm giving a notion of a type being definable. One of these types being definable. That's the idea. So for each formula in phi, we have another formula phi sharp. So remember, formulas in phi have variables x bar, y bar. But for each phi, you have a corresponding formula phi sharp just in the y variables. And this should, it may be some parameters from M. It defines Q, so it's a notion of defining a type if if for all phi in delta, so for each of these formulas phi in delta, and each B bar in B, phi x bar B bar is in Q if and only if M satisfies phi sharp of B bar. So it's a very natural notion of saying that this type is defined. It's saying we can define the set of parameters for which phi is in the type. It's very yes, it's very similar to the usual idea of defining a type. If you like, this is a defining schema for defining a type. You might think of this as like d phi. So that's a common notation, but it's just slightly different, but it's a similar idea.
I don't understand.
Yeah.
If Q can be not be defined.
Yeah, but remember,
You have such formula.
yeah.
Case particular.
Remember, we're talking about always types over finite sets of parameters. And we're only interested in those finite sets of parameters.
About finite sets.
Yeah, yeah. These are types over finite sets of parameters.
For finite sets, it's possible.
Yeah, yeah. So this is a notion of defining a type, a delta type. And the idea then is that the intuition is that if we can define types, then we get bounds on the number of types, because the number of types just depends on basically sets picked out by this. So we get bounds on the number of types, and once you can bound the number of types, you can bound VC density. That's the general idea, that definability of types gives you bounds on VC density. That's the intuition. So I don't want to say too much, because it is a bit technical here. So then we say this definition is a bit of a mouthful, unfortunately. I don't know how, we say delta has uniform definability of types over finite sets. So that's UDTFS in M with D parameters. So that's really what I'm defining here. There's UDTFS with D parameters. If it looks a strange definition, but the idea here for this Q, we had a single family. A single family. So for each phi, there was a formula phi sharp. In order to make an induction work, we want to allow finitely many families rather than one family. So if there are finitely many families Fi, where this is I in I, a finite set, finite index set. So Fi, it'll be a set of formulas like this. So it'll be formulas which we will write in the form phi sub I of y bar and then y1 bar up to yd bar. So this d here, so this is for phi in delta, I guess. So finitely many families of this sort. So for each phi in delta, you have a corresponding formula phi I. Okay, and these are all the same length. So all the same length. So continue the definition. So such that, so this is, I guess this is another definition. So such that for any set B, any finite B inside M to the Y. So that's the uniformity, really. It's the same system of families for any set B of tuples of parameters. And any Q in one of these delta types over B. For any such thing, there are B1 up to BD inside B, and one of these families. So this is choosing one of these families, such that Fi of y bar B1 up to BD defines Q. So in other words, I can define Q putting in the parameters B bar for these y's in the formulas phi I. So it's a strong kind of uniformity of defining Q. That we're allowing, so delta is a finite set of formulas, Fi is a finite set of families, but then for any finite set of parameter tuples, and any one of these types, you can define Q using one of those families with a choice of parameters. It's a little complicated, I'm afraid. I'm sorry. And then, so that's this notion of uniform definability. And then, so final definition, we say that M has the VCD property if any delta x b, so here with x is a single variable, so x is 1, has, I'll say UDTFS of delta xb types over finite sets with the parameters. So the point here is we're asserting that this condition holds for types with a single x variable. That's what the definition is saying, that we can do it with d parameters for types with a single x variable. Okay. I'll keep that. And the theorem is that suppose M has this condition VCD. So we have this uniform definability types with d parameters when x is a single variable. Then every delta, or finite, I guess, finite delta x bar b x bar y bar. So now x bar is a tuple, has UDTFS of delta x bar b types over finite sets types with d x bar parameters. So this is the result which it moves from a single variable x to a tuple of variables x. So that's really the point. You're going from a single variable to a tuple, but rather than having d parameters, it'll be d times the length of x parameters. And it's just a kind of induction. It's counting types. Simple things about counting types when you have definability. Fairly easy calculations, but to set up the induction, you have to have this generality of families, different families, finite families, and you have to, rather than having a single formula phi, you really need to work with a finite set of formulas. So that's a key result. It's not a hard proof. I mean, it's half a page, maybe, or maybe 1 page, but the main difficulty is understanding the definitions. Once you know the definitions, it's a fairly easy proof. Basically, the idea is, you imagine you have a formula phi x, x1 to xn, m, y bar, say. Then you shift it across to phi, replace it as phi x1, and then x2 up to xm, y bar. So the idea is you shift the rest of the tuple to the right, and then use what you know for a single variable. That's sort of the idea, it's this plus induction. Okay, so that's really the key result. As a quick corollary of this, so the corollary, you get that if T has VCD, so this condition I defined here, where you have a single variable x, then m less than or equal to VC density of T of m less than or equal to dm. And I'll just remind for every m. I'll just remind you what that means. To remind you that, so recall VCT of n is the supremum of VC of phi, where phi x bar y bar is a formula in our language, and the length of y bar is n. So it's that's the definition of this VCT, right? So finally, there's a theorem which is quite easy, that T weakly or minimal implies that T has VC1. So T has this condition here with D equals 1. And that's a short argument. Weakly or minimal theories, we can work with one types, because the definition is almost about one types. So it's one paragraph, that's short. And then this theorem is a corollary. So star follows from this. Really, star, this statement here, follows from this fact together with this corollary here. So that's just sort of a sketch of the ideas. So this is a general tool, so we use this also for other examples like the p-adics and so on. And this is, if you have a good understanding of one types, you'd hope to prove something like this, and then you get a general result. Okay, sure. So, yeah, because it depends really on the previous condition. So we're saying that for any, these are always finite. So delta is always finite. And you can think of delta as closed on the negation. For any finite delta where x is a single variable, then you have this uniform definability of types. So you have this condition. So it's saying that you can always do it with d parameters if x is a single variable. So it depended on the previous definition, which unfortunately I've erased the last part of that. But the idea was that for any, we have, given delta, we have finitely many families Fi, like Fi, so that for any type Q, for any B, and for any type Q, you can find some parameters from B and one of those families so that this defines Q. So this is the kind of uniform definability of Q. And then this definition says that for a single variable, you can always do this with d parameters. So d many y's here. So the intuition is that once you know the number of parameters, when you're counting types, you're really counting possibilities for the b's. If there are d parameters, then there are going to be polynomial of degree d choices for the b's. So you get a polynomial bound in the number of b's, and that gives you a polynomial bound on the number of types, and that gives you basically polynomial degree for VC density. It's roughly the idea. I'm afraid that's a bit too technical, but I can maybe tomorrow or Friday I can explain a bit more to you if you like. We can work through it more carefully, but I think that's as much as I can say now. Okay, I'll stop there. Yeah. Yeah, sure. That's it. Yeah. Yeah. Sure. Yes, it was just trying to give you some idea, but it's the same method for other cases as well, or some of the other cases. Yeah, it's kind of reducing to one types. Yeah. Well, really, that you can analyze. I mean, for that final theorem there, you can analyze one types. So, you know what one types look like. I mean, I can go through with you a bit more about how that works, that last theorem there, but yeah. Sure.